तो एक तो फर्स्ट ऑफ ऑल माइक नहीं है तो आई एम ट्राइंग टू टॉक लाउडली बट आई होप द वॉइस रीचेस द बैक इफ नॉट आई वुड एडवाइस कि थोड़ा आगे आ जाओ अगर कभी मैं ऑडिबल ना रहूं या कभी कोई डाउट आए या कभी मैं ज़्यादा फास्ट हो जाऊं मेरे को इमीडिएटली रोक देना ओके वेट आई थिंक आई शुड टॉक इन इंग्लिश राइट
Yes.
Okay, I will talk. Yeah, so if I am not audible at the back, please come at the front. If you do not follow anything or if you have any other issues or any doubts, just stop me immediately. Okay? Continuity is not important. Like you can stop me okay, in the middle of anything.
It was not audible. If anybody wants the fan, just inform me.
Okay. So let's start with a simple thought, okay? Let's try to interact with an astronomer who is 500 years old. Suppose you find an astronomer who is 500 years old and he is working on, let's say, you must have seen the image of the black hole, right? The very recent, very popular image of the black hole. Let's say he was working with that team and he produced that image, okay? And he is very proud of producing that image. There is one way you can definitely make him study. Just ask him what's the practical use. Okay. Ask him, okay, you made this image, okay, he is proud. Then ask him, okay, so what's the use of this image? He will be confused. He will be like, okay, what do you mean? And most likely, he will think back to the time when he was young, let's say 400 years ago, and he would be like, oh, no one dared to ask such questions at that time. No one dared to ask such questions, like, okay, what's the use? So, one thing which is common among all civilizations, overall ages are these. Can you identify these? So these are actually these two. These are from the other side of the world, Americas.
Brazil.
Okay.
Brazil or Mexico?
Mexico, Brazil, yeah. Mexico, both are from Mexico. Okay, this one is from India. This one is Stonehenge, right? The time at which they were built, 200 BC, 900 AD, 1725 AD. Wide variety of times. And this is common for any civilization. Okay, go to Egypt, go to any ancient civilization, Greek. The hallmark of a civilization is that, okay, you have a civilization, that means you have an observatory. That means you have a calendar. Okay, any great empire which has lasted for a sufficient duration of time had to have these things. Okay, and at that time astronomy indeed, so at that time it was not that, okay, we are a curious species, so we will put money into these researches and all. At that time astronomy had to be of practical relevance. Otherwise nobody will get funds. Right? So how exactly did astronomers find themselves landing in that huge amount of money required to build these mega structures? What could have been the use of observing the sky, of tracking motions?
Assigning gods to them.
Assigning gods to them, okay. Okay, yeah, that's true. That's indeed true. So, I think, okay, this was almost entirely ritualistic. Okay, this one was, this observatory was such that it was based on the motion of Venus in the sky. Okay, it was almost entirely ritualistic. But now rituals won't explain everything. So you need some origin of the rituals, or why did people even have that thing in mind, right? There had to have been some extra practical applications apart from assigning gods, apart from rituals.
Keep the track of months, like if winter is coming, we have to save crops, we have to be ready. Keep the track of time.
Seasons for seasons.
For seasons, to predict the time of harvest, to predict when you want to sow the crops, to predict when rain will happen. That's how astrology actually came into existence, right? Astronomers were like, okay, I can predict the seasons. Then they were like, okay, why not other things too? Let's see if there is something else in the sky. other planets, okay, they also move. Let's see, that should be associated with something. Okay, that's basically how the entire astrology came into being. But yeah, it started off with trying to predict the motion of the sun and the moon. Okay, and it was important. And there was another big thing, that was eclipses. Okay, because again that was ritualistic. Okay, you believe, okay, eclipse happens, something strange, and of course strange things, people get scared of that, and you want to predict that. So yeah, astronomers did have a lot of use back then. So let's go on, and I want you all to tell me how many of these terms do you understand? Okay. Which of these terms have you heard before? Which of these terms do you understand? बोलो बोलो नंबर बोलो.
All but three.
How many?
All but three.
All but 3. Okay.
8.
8. Okay. Anybody? I'll just go though. So see, this is what. So I'm assuming that this is your first astronomy talk, right? And I'm assuming that you will start out with understanding maybe neither of it. 0. It's allowed. Okay, that's the thing I will start with. Okay, for many of you it might be your first or second astronomy talk. Okay, so let's start with level 0. Level 1. Okay. Day. What do you understand by a day?
Rotating around its axis.
Earth rotating around its axis. Okay.
Sunrise to sunrise.
Sunrise to sunset. That's okay.
No, sun to
So
next.
yeah, there are 2 meanings of day. So one of them would be sunrise to sunset is day, and then sunset to sunrise is night. But I am talking about the entire duration, day.
No,
The
sunrise to
calendar.
next sunrise.
Huh?
Sunrise to next sunrise.
Okay, now sunrise to next sunrise. Yeah, that's the definition I was taking. Kind of. But does the sunrise, okay. So does the sunrise happen at the same time every day? No minor changes, okay? Okay. So anyway, all these are second order effects, okay? Higher order effects, I would say. So for now, all we understand by a day is, okay, so I shall not be using the board. I shall try to avoid using the board. I shall use these instead. Okay. So what causes day and night? Let me ask you this simple question. What causes the day and night?
Rotation of Earth.
Rotation of Earth, but like, is there any other object apart from the Earth which sun, right? If the Earth would have been rotating but the sun was not there, day and night would not have been there, right? So how do you understand day and night?
Sun above the horizon.
So we see that, okay, the sun goes around the Earth once in every 24 hours, kind of. But what is happening in reality? I think if you have attended the last talk, you would have understood, right? You have the sun somewhere, you have the Earth, and the Earth is basically spinning, right? The Earth is spinning around its axis, and what we see is that, okay, you have the sun over here, so the part of the Earth that faces the sun will have day, the part of the Earth that is away from the sun will have night. This point is clear? Make sense? So this will better show you the rotation. That is, basically this is what is spinning, right? So when this is facing, let's say the sun is here, this is day here, it is night here. And now it's day here, it's night here. Basically the Earth is spinning, right? So now that's our 0th order model or level 1, okay? That basically you have the sun somewhere. Wait, can everybody see this now? Yes. I don't know what to do. Okay, you have the sun somewhere in the sky. Okay, you have the Earth somewhere in the sky, somewhere. Okay, you have the sun somewhere, you have the Earth somewhere, and Earth is basically spinning. Fine. Now you also see the stars and all in the night, right? they also happen to go about exactly the same, which is actually why we say okay the earth is spinning and not the entire sky is spinning, right? It is easier to just say the earth is spinning if everything happens to go around the earth, right? So now our current model is this: you have the sun somewhere, you have the earth which is spinning, you have the stars far off, that's it. Fine? This explains day and night very well. You are happy? Okay. Now, if you look at the sky, then you will also notice some other object over there, apart from the sun and the stars. The moon. Right? And now, okay, for the duration of the day, you say, okay, the moon is somewhere, and now you can also say that, okay, the moon is somewhere, and let's see, the moon is that. So the sun is somewhere, the moon is somewhere, the earth is rotating. Finish. End of story. But what happens is that, okay, look at it the next day. You look at the moon today, look at the moon the next day, and you will find that, okay, it's not at the same place anymore. Okay. So, this leads us to introduce the month. Okay. What we see is that, okay, the moon also appears to move among the stars, and the moon basically seems to be going around the earth. Okay, immediately you can draw this conclusion that, okay, the moon is shifting in the sky and it is going around the earth, and it is going around the earth in about 27 and a half days. Fine. So this is what we have currently: the sun, the earth which is spinning, the moon which is going around the earth. The rate of spinning of the earth is called the day. The rate at which the moon goes around the earth is called the month. The period of the moon going around the earth is called the month. Fine? Fine. Okay. Now what you will notice is that suppose you keep observing the sky every day for multiple days. Okay. You observe it today, you observe tomorrow, you observe day after tomorrow, day to day, day to day, day to day. And let's say the sun sets and you are like, okay, this sky is there. The sun sets, this sky is there. The sun sets, this sky is there. And about in a month or so you will see that, okay, the sky that is here now, the stars, the patterns, they are different from what it was a month ago. The patterns seem to have shifted. Okay. An easier way to put that was, okay, the sun is shifting among the patterns. Okay. So now basically what is happening is that we have basically uncovered the year. So the year is the time in which the sun basically makes a complete round of the sky. So you observe the sky every day, let's say sunsets, you observe the sunsets, you observe the sky go around. Over the entire period of a year, the stars that you will see will seem to basically complete an entire cycle. Okay. Simple way to explain this would be, okay, you have the earth here, you have the moon somewhere here, okay, and you have the sun here. The moon is going around the earth is rotating around its axis, and the sun is also going around the earth once in a year. Fine? Makes sense? Of course, the earth is going around the sun, we know that now, right? But for all the purposes I will be talking today, it will not make any difference. So we will stick to whatever. We will use any model as we see fit. Okay, the sun going around the earth or the earth going around the sun. It's fine. Okay. Okay. Fine. Now I have also split the day and the month into two different categories. So what is this? What exactly happened here?
Solar days with respect to the sun and sidereal days with respect to the stars.
Right. So think about this. Okay. Let's suppose this was the earth. This is the earth, okay? And this is the sun. And the earth is going around the sun. So what happens as the earth spins? It is also going around the sun. So it is spinning, 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 it is spinning. And now one day is over, right? It has spun once. Okay, it was like this, it has completed one spin, right? Agree? This is a sidereal day. It has completed one spin, it was like this, it is now like this, fine. But has a complete day cycle been completed, like the day we define, sunrise to sunrise, or let's say with respect to the sun. With respect to the sun, it would again need to move a little bit more, right? Do you see? It started off like this. Okay, I am exaggerating the year. This is one sidereal day. Okay, and this is one sidereal year when this again points to the sun. It started off pointing to the sun, it points to the sun again. Make sense? Huh? That is one solar day. Fine? Everybody is here with me, right? Sure? Okay. Now, what about the month? Why have I split it into two? Why have I split the month into two as well? Anybody?
Full moon to full moon and complete revolution of the moon are different types.
Exactly. Same logic, okay. Suppose you had the moon going around the earth. Okay. Let's say it started off like this. Okay, the moon will complete its revolution and it will again be like this after one revolution is complete. That's one sidereal moon. Okay. And then it will have to move a little bit more to again come in the same earth, for the earth, sun, earth, moon configuration to become the same. Right? And that sun, earth, moon configuration basically determines the phase of the moon. Full moon, new moon, right? So that thing is the lunar month. Okay, so the lunar month is the phases of the moon. The sidereal month is the position of the moon in the sky with respect to the stars. Fine? So you must have heard, right? The month is 27 and a half days, or sometimes you will hear the month is 29 and a half days. The difference is basically this. It takes 27 and a half days for the sidereal month. It takes a little more for the lunar month, 29 and a half days. And what about the solar day? How long is the solar day? 24 hours by definition. Okay, we have defined our clock so that okay, noon is when the sun is up and midnight is when the sun is below us, almost exactly. Okay, that's how we have timed our clock. So now you will expect that okay, the sidereal day should be then shorter, right? Any idea? Anybody? How would you find it?
After one complete revolution of Earth around the Sun, sidereal year will be 1 day more than the solar year.
Does everybody get his point? Right? Does everybody get his point? No. Okay. So what he is saying is when you count this as the sidereal day and this as the solar day, you wait and keep counting days until you have completed one revolution around the sun. You would have counted sidereal days one more sidereal day than you would have counted solar days. Right? Because this is one rotation extra is being added out here. Right? So basically what you will have. So a sidereal day is just 365.25 upon 366.25 times the solar day. Right? 23 hours 56 minutes. Fair? Now, what else? Is this it? Like, are we done with the model? Right, we have a model which can explain the sky and all now. Okay, fine. You have a way to time your days and everything. What else? Am I missing something? Is there something else that should be in the picture?
Planets.
Planets is fine. Like, recall the terms that I had shown you at the start. Tilt of the Earth's axis, season, right? So, of course, in this simple model, you will have, okay, the sun, the earth is going around, the moon is going around, fine. But what do you see? You see that, okay, for one half of the year, the sun appears higher up in the sky than the equator. Okay, it does not appear like this. It appears, sometimes it will appear higher up in the sky. For other half of the year, it appears lower in the sky. Okay, the days are shorter, everything it follows, and it is colder, so it's winter, and we call the other half summer. Fine. Now what new? So how would you put this into the picture?
Tilt of the Earth.
Tilt of the earth, right? So you start out with the sun, you have the earth, and now your earth is not just spinning like this and going around the sun. It is spinning tilted. Okay, this is the way in which it is spinning. Fine, and it is going around the sun. For this half of the year, you will have this side facing the sun. The sun will appear higher up in the sky for people living in the north, and it will be summer in the north. For this half of the year, people in the north will be facing away from the sun. The sun will appear lower in the sky for them, right? and it will be winter for them. Clean? So this has taken us to, sorry, what happened? Okay, this has taken us to level 3, sorry, level 4, inclination of the Earth's axis and seasons, right? So now we missed a side quest on the way here. Batao. So tell me, do you have these three terms are extra? Okay, now can you explain tides? Okay, given what you know, can you explain tides?
Effect of the moon and the sun's gravity causes deformations in the patterns of water distribution over oceans.
Yeah.
It's not spherical, but it's higher at some places, lower at some places. It changes the energy.
Right? Acha, so for those of you who don't still understand, the reason, okay, this one again involves gravity. The understanding came about much later, but we could predict tides much earlier. Okay, keep that in mind. So we could simply predict tides because we knew that okay, the sea level is high when the moon is exactly overhead or exactly underneath. Okay, exactly opposite to where we are facing, the tides are high. Okay. Sun had a little influence on the tides, not much. Fine. So basically, the reason it happens is you have the Earth and the Moon. They are basically gravitationally attracted to each other, which is why they go around in circles. Fine. Now the way they go around in circles is such that the acceleration of the Earth basically is equal to the gravitational force, the net gravitational force of the Earth. Right? Fine. So now in the frame of the Earth, you don't have that thing acting as a pseudo force or anything. Right? But if you look at the point on the Earth that is closer to the Moon, okay, it will be experiencing a larger force due to gravity, and the point on the opposite end of the Earth will be experiencing a lower force due to gravity, right? Now the Earth is accelerating around the Moon, so the net effect of gravity is cancelled, but this higher effect and the lower effect, the difference remains, right? And the effect is basically that the Earth is squished or it is stretched in the direction of the Moon. Okay. And because the solids can't deform much, water deforms more easily, we basically have tides. Okay, the Moon is pulling, the Earth is going around, there is a deformation like this, water deforms, land doesn't, you have tides. Simple. Okay? Chalo, let's move on. Okay, also you see the same face of the Moon every day. Right? What happens? We call it tidal locking. You all must have heard that term, right? Have you heard of the term tidal locking? So how exactly does it work?
The side of the moon closer to the Earth faces more experiences more gravity, so prevents the moon from rotating with respect to the Earth.
Okay. Yeah.
Sort of total friction.
So basically the same effect. Okay. The moon is also being stretched by the Earth's gravity. Okay. Now if the moon were to rotate with respect to that stretched configuration, it would basically take away energy. Right? Because we are basically squishing and stretching the moon. Just as we are, like what is happening with the Earth, right? Tides basically dissipate a lot of energy. Huge amounts of water are being moved around. Right? So if your moon was also to rotate, that land which is stretched by the Earth would also be squished around. And energy is dissipated. And ultimately that dissipation caused the moon to basically align itself with the Earth all the time. So the moon is stretched and it does not have to basically deform over and over. It is deformed in one way and it will remain that way for a long time. Make sense? Okay. Now, this last thing is a problem for you. Okay. So it turns out that suppose if we send people on the moon, and let's say that guy who is living on the moon has a friend on the Earth. Okay. And he wants to talk to that friend every day. Okay. Then that person on the moon should have a 25-hour sleep cycle. Do you get what I am saying? One person is on the moon, another person is basically present on the Earth. Okay. the person on the moon wants to communicate with the person on the earth when he is awake. Okay. So this person on the moon should have a 25-hour sleep cycle. Can you use what you have just learned to explain this? Anybody?
The Earth completes one rotation with respect to the Sun in 24 hours, but then again the Moon will be moving a small distance, so the Earth needs to cover that.
Exactly.
That requires another hour.
Right. Okay. So basically, let's say this is the person on the earth, okay, and there is and this is a moon. So what is basically happening is that as the earth is rotating, the moon is rotating around the earth, revolving around the earth. Fine. So you basically have something like this. This is 24 hours. Fine. You have something like this being 24 hours or 23 hours 56 minutes. Okay. And the moon has been slightly moved, like the moon has moved ahead in that time, right? So you will need extra 1 hour to complete that and again be facing that person, right? So that's why you would want to have a 25-hour sleep cycle when you are on the moon, so that you can communicate with the same place on the earth daily. Make sense? Anyway, these were just some interesting things. So let's get back here. What's the inclination of the earth axis? 23.5 degrees, okay. This should be like, you must have learned this in school, right? And seasons, okay, fine, we have completed seasons. So actually it's a matter of notation, but yeah, usually in astronomy, we do not call this half to be like, let's say this. We do not, if you have the sun, we do not call this half to be winter and this half to be summer. We actually call this half to be summer and this half to be winter. Or to be fair, we divide it like when you are facing towards the sun, till when you are exactly perpendicular. Okay, you are not facing towards or away from the sun. This part is summer, this part is autumn, this part is winter, and this part is spring. Fine. This is just how we divide it. Okay. So we would want our year to be basically aligned with that. So we can basically tell when our crops have to be sold and everything. Fine? Okay. So inclination of the lunar orbit. So what is wrong with this with this ready model which we have is that according to this model, you would have eclipses every time there is a full moon or a new moon. Right? The sun is going around the earth, the moon is also going around the earth. So why don't we have eclipses every time you have a full moon, as in the moon is opposite to the sun in the sky, or a new moon, as in the moon is in the same direction as the sun? Right? Because, come on, like you would have the shadow of the moon falling on the earth or the shadow of the earth falling on the moon. Right? So why don't we have eclipses every time? Exactly. So that is what we refer as the inclination of the lunar orbit. Fine. How much is the inclination of the lunar orbit? 5 degrees. So now, we basically now have our almost completed model. Right? At least it is good for all purposes except one. Okay, I will talk about that. So suppose this is the plane of the sun. Okay. The Earth's orbit, let's say. Okay, this is the plane of the Earth's orbit, or in our view, it is the plane in which the sun is going around in the sky, right? The Earth is basically tilted like this, spinning around its axis. The moon's orbit is also slightly tilted off by 5 degrees. Okay, and it is also making its orbits around the Earth. So now what can happen is that on the new moon, the moon would be somewhere lower in its orbit. Let's say the sun is over here, and I have a full moon like this. When the moon's orbit is inclined like this, will I have an eclipse? No. And I will exaggerate it a little bit. No. What about if I have a full moon when the moon's orbit is tilted like this? No. But what if I have a full moon when the moon's orbit is like this with respect to the sun? You would have an eclipse, right? And like at this time, you would have an eclipse as well. right? So now you basically have your model that your Earth is spinning, your moon's orbit is tilted, fine, everything is going around the sun in this plane. Is this model complete? Is this model complete? No, just Earth, Sun, Moon. Is this model complete enough? No. If you go with this model to an ancient period, let's say you time travel, you would basically be beheaded. Not because saying that the Earth goes around the sun, that was actually quite accepted back then. But because this model will actually fail to predict eclipses in any manner. Okay, so there is actually a famous folklore, I don't know if you have heard of it, but in like the 10th century, or maybe before that, there were two Chinese astronomers in the court, in the court of ancient Chinese emperor, and because they failed to predict an eclipse, they both were beheaded. So, okay, now let's think about what this model has to say for eclipses. Fine. The moon's orbit is tilted. Okay, I will forget the Earth for a moment. The moon's orbit is tilted. Now, as this tilted orbit basically goes around the sun, if there is a full moon in this region, you will have a lunar eclipse, right? If there is a new moon here, you will have a solar eclipse, right? Somewhere here. Now, you won't have any lunar or solar eclipses, no matter what full moon or new moon. Here, you can have solar or lunar eclipses, right? Because again, it's in a plane, it's cutting off exactly like that time. And again, when you are like this, you won't have any lunar or solar eclipses because the Earth shadow and the moon shadow will basically not intersect. Fine? Everybody is clean on this point, right? When your moon's orbit is tilted, you can have eclipses in this period. You can have eclipses in this period, right? But you can't have eclipses here, here, or anywhere else. There will be a small window here, there will be a small window here, right? And if you have a new moon or full moon in those windows, you will be able to have eclipses. Clean? Fine. So there should be like two oppositely spaced months of the year when eclipses happen, and eclipses should not happen on any other month, right? Right? Is there any such thing in existence? No. Solar eclipses basically happen randomly. Tell me the date of the next solar eclipse.
Next one happens, the total one happens on the 2nd of August 2027.
2nd of August 2027.
Yeah.
And when did this eclipse happen?
April 8th this year.
April and August, come on. April either sun or August here. How did it work?
Inclination of the moon's orbit will change.
Not the inclination, but yeah, you are on the right track.
Like the plane of that will change.
The plane will change. Okay. So now let's check out. So these are the solar eclipse dates. The red ones are total or annular, both of them. The blue ones are partial. Okay. So now you can see that, okay. Where did I? That, okay. Around, if you are in the 1980s, the eclipses are basically happening in August. Right? If you go in 1985, your eclipses are basically happening in June. Go to 1990 and your eclipses are basically happening in February, right? The dates of eclipses, or if you just plot out this graph, okay, you basically see these straight line fits which happen very naturally. Okay, these straight line fits basically tell you that, okay, if your eclipse happens right now, then its position in the year basically gradually changes over a period of 19 years. Okay, if you start out, let's say here, then you will end up here in 19 years. Okay, the gap between this point and this point is 19 years. Okay, so what does this mean? Is that basically your moon's orbit is like this, but it's also gradually shifting in this manner, right? So that when you have an eclipse, like let's say you have an eclipse now in this particular location, this particular time of the year, after some time you will have an eclipse actually in this particular time of the year, slightly ahead, then slightly ahead, and basically because your moon's orbit is not in the same plane anymore, the inclination doesn't change, okay, just the plane changes like this. Okay, this is actually very much in analogous to this top. Okay, so if you have a top like this, the inclination of the top is not changing. Okay, it is increasing gradually due to friction, but basically the plane is revolving. Do you see what is happening? It is kind of like this. The inclination won't change, the plane changes. Somewhat like this. And hence the month in which the eclipse happens also changes. Fine? So this leads us to introduce the period of the draconic month. The draconic month is basically the time between the moon crossing. Okay. So you will have this plane. Okay, you will have this plane intersecting the plane of the sun. Fine. The moon will cross this plane once in its orbit, and if this orbit were not changing, it would again cross this plane again after a month, right? If the moon's orbit were not changing, it would cross this plane once every month, right? Upwards, not downwards. Like upwards, downwards, if it would twice a month. But now, because the moon's orbit is also shifting, it takes a little bit extra time to cross that plane. Okay, and the draconic month is basically the time between the moon be crossing two ascending nodes. Okay, ascending nodes is basically this, the point where the moon's orbit cuts the sun plane, earth sun plane. Fine? Following me up till this point? Yes? Yes. Okay. So now, any other issues that you find with this model? So this model is actually pretty accurate, and this was actually used by ancient astronomers for a long time. Okay, any corrections onto this model are actually pretty modern. Okay, but they are sufficient enough to be considered. Okay, so now let's look at the tale of two cities, or maybe two empires across the world. Why am I not being able to advance this slide? Okay. So there was the ancient Indian civilization, right? And there was the Roman Empire, right? There were a lot other empires, but we'll not go into that for now. What we want to compare is how these two cultures measured time. Make sense? Okay. So the Roman calendar actually existed for a long time in the ancient Roman period. Some of you guys might have been interested in history, right? Okay. So now what happens is that the ancient Roman Empire, basically there is a succession war and Julius Caesar ultimately takes the throne. Immediately after that, Julius Caesar realizes that okay, all these old Roman calendars which are circulating, they need to be unified and they need to be made more accurate. So he introduces the Julian calendar, or in this case I am talking as a Julian correction to the Roman calendar. So how does the Julian calendar work? Anybody? That's the calendar we use. I mean, almost. Gregorian, yeah, I mean, almost. So the Julian calendar is basically this: 365 days in a year, divided into months somehow. Ignore the moon. Okay, ignore the moon. 365 days a year because okay. And then he realized okay, we need some accuracy. We will be losing some dates. So he's like okay, once every 4 years, add a date. Make sense? Very good. The calendar was actually being used. This correction was made in 46 BC. 46 BC. Okay. And then what happened is that for, like as I said, any corrections further would actually take a long time. So for ancient astronomers, this was content. The model we had before was content. But now what happens is that in the 15th century or 16th century, 16? Okay. Pope Gregory basically realizes that okay, we are far off. So basically they have a festival called Easter. Okay. You must have heard of Easter, right? What is, does anybody know the definition of Easter? So what you do is you wait for the vernal equinox. When the vernal equinox is done, what you do is you wait for the first full moon after the vernal equinox. And I think it's a Sunday, right? So you wait for a Sunday nearest to the full moon after vernal equinox. Okay, that's basically Easter. And what Pope Gregory realized is that okay, now Easter is very far from the real vernal equinox. So I need to change my calendars. And so he had some astronomers and he calculated some corrections to the calendar, skipped some days and brought the calendar back in sync. Okay, what was his Gregorian correction as we call it? Anybody? You.
Every 100 years the leap year would be skipped, but every 400 years the leap year will be back.
Right. Does everybody agree with this? Years that are a multiple of 100 are leap years only if they are also multiples of 400. Okay. So can you tell me what duration of the year these people ultimately over the years came up with? Let's do a quick calculation. Okay. You start out with 365 years. Okay. Now what you do? Every 4 years you add 1 day. Right? So 365.25 days per year. Right? Now what?
Subtract 1 year every 100
years minus.
Subtract 3 days every 400 years. Okay, so what will that number come out to be? I think it's 365.242 something. Okay, and ultimately there are some other corrections as well. So, like beyond this time, what happened is that as modern astronomy came into the picture, Herschel finally proposed his own correction, which is that years that are a multiple of 4000 will not be leap years. Okay, that was Herschel's correction. And ultimately this calendar still describes our seasons very well, right? So what this calendar has managed to do is that this calendar has managed to keep the track of winter solstice, Easter, or as you say, vernal equinox, autumnal equinox. Basically it has managed to keep track of the seasons for around 2000 years. Okay. Now let's talk about the Indian calendar. And before that, let's have a little bit view on the zodiac as well. So what I started out with is that there are stars that are very, very far away, right? So now, basically what we said is that, okay, all the stars that are in the plane of the sun, we basically broke them down into little constellations. Okay. Zodiacs. We broke down some patterns into them and we called them zodiacs. Fine? That's all you need to know. Now let's look at the Indian solar calendar. Can anybody tell me what you know about the Indian calendar? You must have used it somehow, right? Anybody?
A lunar month starts. A lunar month is defined as starting from a new moon or a full moon, depending on the culture, within a particular zodiac period. So there might be 2 lunar months in a single period, or there might not even be 2 lunar months called Adhik Mas or a related Mas.
Right. So basically what the Indian calendar does is, okay, we will track the months according to the moon. Okay. But then they say, okay, but we will keep the year according to the sun, independent. Okay. The simple thing is, okay, if this is a new moon, what you do is you see when the sun is, where the sun is in the sky. If it is in so and so constellation, you call that month Chaitra. And if it is, so Chaitra, Vaishakh, Jyeshtha, Ashadha, basically it goes like this, you must have heard, right? And now what happens is that because the month is not an exact integral multiple of the year or a divisor of the year, you will have maybe 2 times the same month. Okay, the sun was in Chaitra, now after one period of the moon the sun is still in Chaitra. So in that case you repeat a month or you subtract a month depending on that. And what the Indian calendar was able to do is that it was able to track the sun's motion in the stars accurately. Okay, because come on, basically the moon was just there for a kind of showpiece. Okay, but it was able to track the sun's motion among the stars. So Chaitra would always be that, okay, the sun is in the constellation of Chitra again, over and over and over and over and over again. Fine. Now because we track the months from full moon to full moon, what happens is that you must have seen that the dates of the festival basically get shuffled around randomly, right? But there is one festival in the Indian culture which does not get shuffled around randomly, which is the same day with respect to, almost the same day.
14th of January.
कौन सा? मकर संक्रांति, right? Agrees? Everybody agrees? We also call this as Uttarayan, right? So does anybody have any idea of why we do this?
Like the sun changes its annual track, and like Uttarayan because it starts towards Uttar. And Makar Sankranti because it actually is present in the constellation of Capricorn. Like it's the shift between Sagittarius to Capricorn.
Right.
But again, it has shifted later on because.
So Makar Sankranti basically means Makar is Capricorn. Okay. So Makar Sankranti basically celebrates that okay, the sun has passed the first point of Capricorn. Okay. Now what was that? Like in the olden days, first point of Capricorn. So let's say this is the Earth, okay, and this is the sun. Fine. First point of Capricorn was basically when the Earth was pointed exactly away from the sun, when the north of the Earth was pointed away from the sun. Okay. At that time, the stars that were behind the sun in the sky were belonging to the constellation of Capricornus. Okay, there were certain stars in the sky, and the first point of Capricornus is the point in the sky at which time the Earth was pointing away from the sun, the point exactly behind the sun. Okay, or the point on the sky where the sun is was called the first point of Capricorn because it existed in the constellation of Capricorn. Fine. So every time the Earth basically passes this point, what happens is that the sun was going southward in the sky, and after passing this point, the sun starts going northward in the sky. Right? Make sense? So that was basically why we called it Uttarayan as well, right? But now tell me, when does Makar Sankranti happen?
14th of January.
14 Jan, 15 Jan, fine. But when does this point happen?
Presently,
22 December, right? So now what has happened is that suppose that's the Makar Rashi, okay? Before the Earth's rotation axis was like this, okay? So every time this was the Makar Sankranti, Uttarayan happened. Now the Earth's rotation axis has basically tilted before. So now this is 22nd December, Uttarayan starts, then Makar Sankranti happens, right? So what does this mean? That the Earth's rotation axis is not a constant. It has been tilting very, very slowly. So slowly, in fact, it was like how many days? 27. Right, 27 days. No. 15 plus 7, 22 days. Okay. It has tilted up by around 22 days of a year. Okay. In the entire duration of the like 2000 years. In about 2000 years, huh?
So current calendar is 2000 years old, but we have been calendar keeping since 7,000 years.
Okay, 7, but no, this has happened. Yeah. So what has happened is that roughly this shift of 1 month has happened over the period of 2000-ish years. Huh. Okay, but like this shift of 1 month basically from 22 December to 15 Jan, about 1 month, has happened in 2000 years. Okay, now you can simply extrapolate this motion and you can see that okay, this Earth's axis will basically complete an entire precession cycle as we call it. Okay, again the tilt of the Earth's axis won't change. Okay, it will remain roughly the same. But the direction in which the tilt is will basically complete an entire cycle once every 26,000 years. Okay, you can arrive at that number a little bit yourself, right? In around there was a shift of around 1 month in the calendar over a period of past 2000 years. So how much time will it take for our calendar, Indian calendar, to be shifted by 12 entire months? 24,000 years, right? But of course it was not exactly 1 month, so the exact number is 26,000 years. Make sense? Clean? Okay. So now this actually will introduce us to two concepts of the year, the Indian year and the Roman year. Which year will you use to calibrate your seasons? Roman, right? So what we call is the first one we call as the sidereal year. The position of the sun among the stars repeats. Okay. This basically means that the earth will have made one complete rotation of the sun in that much amount of time. But it will take a little bit more time for the vernal equinox or any season months to align, right? For the vernal equinox. So the point between two vernal equinoxes is what we call the tropical year. Okay. And the point between the sun falling at the same position among the stars is what we call the sidereal year. Okay. Because of this difference, we actually see that the sidereal year is a little bit longer. It is 365.25 or something. I'm not sure. Okay. This difference is what has caused this to happen. Okay. Now we are almost there. Like we are there. You have your calendar which survives for 2000 years and everything. But there is still one thing. There are still one or two things which we have not yet explained. You observe it yourself. You must have heard of it. You have definitely heard of it. Anybody? This entire model is fine, right? Fine? Achha, any doubts in this model? Achha, we'll take a little time here. Any doubts up till this point? No? Sure. So what have we not explained yet? What other observations do you make that we have not explained yet? Also, I have pulled out a sleight of hand up till now. Can you identify that sleight of hand? Vivek? Anything?
None that I can recall at the present moment.
What?
None that I can recall at the present moment.
Sad. I thought you would be the first to point it out. Precision is this, right? This is precision.
But we have rotation.
And mutation, okay. Mutation happens over a much longer time. Not that. You have observed it. Like you must have seen it in your lifetime. You must have seen it in the news. You know it. You know it. You get mad over it. There is one weak link that I have pulled off, and there is one unexplained observation that I have not yet mentioned, but you would have known it. You knew it. Oh.
So some eclipses are not, and some are annular, some are total. So you didn't mention.
Some eclipses happen like that, some eclipses happen like this. Right? Why?
Elliptical orbit of the moon.
Elliptical orbit of the moon. Right? So the moment you start off with this, you will immediately be like, okay, the moon has, you can start tracking the angular size of the moon in the sky, and you will find that, okay, it's not the same. So the moon's orbit is not a circle, it is coming closer to the earth and it is going away from the earth. Make sense? Make sense? So, this will lead us to another issue, to another definition. Okay. So that basically, wait, I don't recall. So you can actually have another month like this. The moon is at perihelion. Perigee. The moon is at perigee. Wait for a month, the moon will be back at perigee, right? But of course, the moon's orbit, the ellipticity of the moon's orbit itself rotates. So you can have a new definition of the one, perigee to perigee. Right? You can name it something else. I have not put this here. But yeah, you can have this other, I think it's called the anomalistic one. Okay. Now what about this other observation? Can you tell me what is present in that photo? Snapshots of the sun at a particular time. So this image is basically what you get if you train your camera at a specific, you just place your camera on the earth, point it at some position, and then take a picture once every day. Okay, every time it's 3 o'clock, take a picture. Every time it's 3 o'clock, take a picture. And over the period of a year, you will notice that the sun basically goes around like this. Okay, the sun's position at 3 a.m. is not 3 p.m. or some any other random time. I think this was 3 p.m. is not a constant. Okay, the up-down motion you can understand, right? Because the sun was higher up in the sky, the sun is going lower down in the sky. What about this motion? Right, there is some motion in this direction as well, right? So here was a little bit of light off and I have pulled off. Light on pulled off. So we have basically defined day as a period of 24 hours, right? How did we do that? Because okay, the sun is also going around the star, so the earth should point at the same direction with respect to the sun. This we did when we did not know anything about inclination and all. Like we didn't consider inclination and stuff in the picture, right? So now, basically, let's do something. Okay. This is okay. What I'm going to show now is not like this is a sphere. Okay, consider a hollow sphere. I have cut it off and I am looking at the inside of the hollow sphere. Okay. So this is basically the inside of the hollow sphere. Make sense? Okay, the hollow sphere, this is basically the inside. Let's then not do this. Something like this. Okay, this is like the center. Okay, so the day we defined was basically with respect to something we call the mean sun. Okay, the mean sun is a hypothetical object that goes around in the sky once every year. Okay, in the plane of the Earth's rotation. Okay, it goes around in the sky uniformly in the plane of the Earth's rotation once every year. Make sense?
Rotation or the revolution? Is it rotation or revolution?
Plane of Earth's rotation. Okay, like this was before before I even discussed axial tilt and all. Okay, at that time we had this definition of a day, right? So basically this is the Earth's rotation, the sun is going around like this once every year. Mean sun. Okay. Hello. Okay. Okay. So now what we did was we tilted the Earth's axis, right? After that. So what change we have done is that now this was the mean sun. Okay, mean sun. I will use a different color. There was a black, no? The true sun, basically we have seen that okay, it goes like this. And then it comes back on. Right, this was the mean sun. The true sun basically goes at a tilt. Make sense? Now, suppose the true sun was also going uniformly in its path. Okay. And we were to take a photo of the true sun which is going uniformly. Okay. Abhiketi will assume it's going uniformly. What shape would we have seen in the sky? No. No. So even if it were going uniformly, it is going uniformly around this circle, right? Okay. Will its project, so, and we are taking photos at uniform intervals among this position, right? Our mean sun is stationary in our photos. Make sense? Our mean sun is stationary in our photos, right? So we basically in our photos the position of the sun will be the position of the true sun with respect to the mean sun. Make sense? So you are saying, so the fact that it would be a straight line, this argument depends heavily on the idea that if you are going uniformly around this point, that means your projection is also going uniformly around this line, which is not true. So this the sun speed along this is also once a year. The sun speed along this is also once a year. Okay. What is the projection? Like, so if I try to track this motion, I project it along this line here. At this time the motion is slower, right? The motion of the projection of the true sun is slower than the mean sun, right? Because there is a cos angle, cos of 23.5 degrees associated with it, right? Make sense? Perfect. So that means this is vernal equinox, right? The sun is going higher up in the sky. Vernal equinox. So from vernal equinox, it is going higher up in the sky, and it's also lagging behind. Right? It is lagging behind. Huh? Okay. The mean sun is a hypothetical object we define that goes around the earth in the earth's axis of rotation, along the earth's plane of rotation, once a year. Fine. The true sun, for now, the true sun goes around the earth, but in a slightly tilted fashion, 23.5 degrees tilted. It also goes around the earth once a year, and for now uniformly. Make sense? Clean? So now tell me what you would expect. So the projection of the true sun will be slower than the mean sun around the vernal equinox, right? Around the vernal and the autumnal equinox, both. Okay, and it will be faster than the mean sun when it's near the solstice, because if you are near the solstice, let's say you are going with some speed, your projection from the pole to the equator is basically going to enhance that speed. Make sense? Because like this is, let's say this is the surface of a sphere and you go like this, you would have traveled a larger distance along the equator, right? If you just take your projection, your projection would have moved larger distance. So what's basically happening is that the mean sun will be going slower to the true sun and northwards, then it will take over, then it will come back, it will take over, then it will again be slowed down, then it will again take over, and then it will be again slowed down in a fashion like this. This being the summer solstice, this being the winter solstice, this being the vernal equinox, this being the autumnal equinox. Top to bottom, bottom to top. And again, over a period of 1 year, it will be back. Because, come on, the true sun and the mean sun are both going uniformly, they have gone their different paths and they are back. Make sense? Make sense? So now, this is what you should have seen, right? So instead of this line, there is another effect here, sorry, in the opposite. So this is what you should have seen, right? But now what do you see? Is there any difference? Additional difference? Size. They are not symmetrical. Why is that? Huh? Because of the ellipticity of the sun itself, right? Now tell me, which of these terms do you understand? How many of these terms do you understand right now? Sorry, I forgot. The anomalous here is basically perihelion to perihelion. Okay? Because now you have this, you know that okay, the Earth's orbit is eccentric. You start from a perihelion, you get back to a perihelion, and that is called an anomalous period. Fine? So tell me, which of these terms do you understand? Like how many of these terms do you understand now? Number. I hope all of them understand them, right? So now, okay, I will end this with a little bit of a random discussion if we have time.
Hemansh, there was a question.
Anomalous month. Okay, I'm not sure if that's the term, I'm just guessing, but it's. Right? Oh, anomalous month. Okay, I will tell it. Ah, fair enough. So basically, it's like your moon's orbit is eccentric, right? So the perigee of the moon's orbit back to another perigee of the moon's orbit is the anomalistic month. Okay. Basically one complete orbit, but not really, because so what basically happens is that the perihelion of the lunar orbit and the perihelion of the Earth's orbit around the sun, they also precess. So yeah, that's what I wanted to talk about now. Why does precession happen in the first place? So do you understand why the top precesses? Okay, it has started precessing. Why does it precess? Does anybody I think most of you understand why top precesses, right?
It acts like a gyroscope.
It acts like a gyroscope. Kind of, yeah. But now tell me, so why does the top precess? So the simple thing is, suppose the top is rotating like this, okay, it is spinning like this. Its angular momentum is in this direction, right? The Earth's gravity is basically pulling it downwards, but like it is fixed around this point. So if I talk about the torque is like this, right? And the torque is the rate of change of angular momentum. So the angular momentum is basically being pushed like this. It's moving in this direction. So what does that mean? It will have to go like this, and that would basically cause the torque to precess. Now the point I am asking is, what applies the torque for these objects? Why do these things precess? Why does the Earth tilt precess? Why does the lunar orbit precess? How much? Why? They are in space, okay? So, what is the mechanism by which they are being made to precess? Gravity?
Probably gravitational.
Okay. But how?
The axis is tilted and then gravitational force on both points is different
Fine.
on the top and bottom of the axis.
But how does the torque arise out of it?
So
Does the Earth not being exactly spherical in shape, that is the reason for the torque?
It has to come into the picture, right? Because if the Earth was exactly spherical, there is no way gravity could have applied a torque on it, right? So what is basically happening is this. Your Earth is like this, highly exaggerated. Okay, your moon is here. Now, what is the tidal? The Earth is basically accelerating freely under moon's and the sun's gravity, right? Right? But what is the tidal force? There is some tidal force, right? The moon is basically pulling this Earth here, it is pulling this slightly less, this is pulling more, right? Now the acceleration of the Earth will basically have removed this main component and there will be a little bit thing left here, right? And what is this doing? This is basically applying a torque like this, right? So the Earth is rotating like this, there is a torque like this due to the presence of the moon that will cause the orbit to axis of rotation to precess. What about the precession of the orbit of the moon? Similar principles, but it is basically the sun whose tidal force acts. So basically, this is the Earth, this is the sun, and this is the orbit of the moon. What is happening? The sun is basically, when it's here, there is an extra tidal force in this direction, and when the moon is here, there is an extra tidal force in this direction. Averaged out over an orbit, there is a slight torque, right, which will cause the orbital plane to precess. Make sense? So now, okay, let's talk about the precession of perihelia. Okay, why are the anomalous month and the anomalous year different from these other terms? From the sidereal month and the sidereal year? Why do the perihelia precess? Any idea? perihelia or perigee, whatever, why does it precess? I mean, because the force was not exactly 1 over r square, right? Okay, this is direct, right? Because if the force was exactly 1 over r square force, the perihelion would basically come at the same time. Okay. Now, what can cause the force to deviate from 1 over r square? So, interestingly, Newton had his other idea that he thought that there was some other force coming around. Turns out that was not the case, of course. There are other planets, right? Which can perturb it, they can change the force law. There is some extra terms out there. And that will basically make the perihelia not to come at the same place again and again. Fine? So that's how the perihelium precesses, that's why the moon's perigee precesses. Okay? Now, final. Okay, now what's the final thing? I also want to tell you one thing. So, one of you, I think you pointed out that the Earth's, even like up till now what I was saying was that the Earth's tilt remains fixed and basically the plane of the tilt rotates, right? Once in 26,000 years. That was what I have been told, right? Like that's what I have told you. But it turns out that the tilt also changes. Okay, it also basically the tilt increases, decreases, increases, decreases over a period of around 41,000 years. Why is that? Why is that? Chalo, guess. Not really.
Is it because the Earth being not spherical and the sun scatters force will like?
So the thing was, I posed this question in a confusing fashion. I said, why does the tilt of the Earth's axis change? Now, just dig down into this question. What am I actually asking? I am asking the tilt of the Earth's axis with respect to the Earth's orbit. Right? Why does it change? How am I measuring the tilt of the Earth's axis? I am measuring the tilt of the Earth's axis with respect to the Earth's orbit, right? What could happen also is that the Earth's orbit could be tilting up and down, with the Earth's spin not tilting that much. So we would still see that, okay, the inclination increases or decreases a bit, right? Right? It turns out that Jupiter's orbit is 1 degree tilted to the Earth's orbit, right? And now it's natural to expect that, okay, Jupiter will cause the Earth's orbit to precess off its axis, right? So the Earth's orbit is, so basically, this is Earth's orbit, it's like 1 degree tilted, this is Earth's axis which is nicely tilted, and now this orbit is itself precessing, 1 degree it's precessing off. So the Earth's tilt, even if it's held constant, it will vary a little bit, right? That is what basically causes this thing. So that's a 41,000 year thing. Okay. And what about the Earth's perihelion precession? Over what time scale does that happen? Over 1 lakh years. Okay. And not just that the perihelion precesses, the Earth's orbit also increases and decreases in its eccentricity due to Jupiter and other planets' influence over a period of 1 lakh years. Okay. How can we verify it? We look at the geological record. Okay. Fluctuating temperatures, ice ages, everything is corresponding to this. Okay. So that's basically, I would say that's it from my side for today. Okay, you understand the dynamics of the Earth, Moon, Sun system. Basically, this is almost all practical application of astronomy, apart from, of course, going to space and stuff. Okay.